and welcome to another episode of the Data Science Decoded podcast. I am here with Nir and Mike after, I think, 2 weeks, 3 weeks of a short hiatus. So how are you guys?
I'm
good.
okay. Nir, now you start.
Yeah, Nir.
Okay.
Start.
All right. Yeah, doing good. Doing good. Can't complain. Looking forward for discussing the expectation maximization algorithm.
Yeah, I am also okay. I missed you guys. I think the last episode we recorded it was 3 weeks ago and not 2, as far as I remember. And let's talk about AM. Let's dive in.
Perfect. So I'm also okay. Thanks for asking. I'm in Boston, so it's freezing. I'm visiting MIT. It's minus, I think, like 28 Fahrenheit. Or minus, that's a funny story. It's minus 18 Fahrenheit. Yeah. So today we are going over the let's say, the least old paper in the history of our podcast. It's from 1977. The title is Maximum Likelihood from Incomplete Data via the EM algorithm, the Expectation Minimization algorithm, which is quite famous. It's by AP Dempster, Nan M, Laird, and DB Rubin. So all of them were at Harvard back in 77, 76. Rubin is famous for his causal inference framework. So that's most of the work that is done, is the idea of counterfactuals. So if you want to calculate the causal effect, you need the counterfactual of the thing that really happened in reality. And he built a mathematical way to formalize that. As that's as far as how I know him. He's still alive. I think all of them are still alive.
Okay.
Yeah. And I'll read the summary or the abstract. A broadly applicable algorithm for computing maximum likelihood estimates from incomplete data is presented at various levels of generality. Theory showing the monotone behavior of the likelihood and convergence of the algorithm is derived. Many examples are sketched, including missing value situations, applications to grouped, censored, or truncated data, finite mixture models, variance component estimation, hyperparameter estimation, iteratively reweighted least squares, and factor analysis. Cool. So the idea, we won't delve in all the derivation in the paper. We're going to go over the main important points and have a discussion. And prior, Nir, you told that some of the derivation were later discovered to be incorrect. So if you can tell us a few sentences about that and how did you heard about it, etc., that would be nice.
Yeah, I think I read it in when you send this paper for us to go over. I googled it and I read about it, probably in Wikipedia or others. And it's not that everything was wrong. It just the convergence analysis, it had some flaws, and the convergence analysis of the expectation maximization algorithm, it had some flaws, which was then corrected, I think, a few years later.
Yeah. So
also,
the algorithm is okay, but some properties of how it converges, different situations, there were mistakes there.
Because
the
chapters
algorithm
1
is
and
okay
2,
because tens of thousands or maybe hundreds of thousands of people use it and got very good results from this algorithm. But
yes, definitely.
Cool.
Yeah,
So I'll read
the algorithm is good. Yeah.
I'll read the introduction of the first chapter. So they say this chapter presents a general approach to iterative computation of maximum likelihood estimates when the observations can be viewed as incomplete data. So to our listeners, our first episode was Fisher's paper, and we discussed in depth the concept of maximum likelihood. So it's a reoccurring theme in data science, machine learning. That's like the basic tools you need to understand. And here they say, okay, what happens when I don't have all the observations that I need in order to calculate the maximum likelihood, right? And that's what they call incomplete data. And they say, since each iteration of the algorithm consists of an expectation step followed by a maximization step, we call it the EM algorithm, right? So usually maximum likelihood is only maximization. So now they added another step. You calculate the expectation of the things that are missing, of the missing data, right? So in a sense, it's quite intuitive. And they say the EM process is remarkable in part because of the simplicity and the generality of the associated theory, and in part because of the wide range of examples which fall under its umbrella. When their underlying complete data came from an exponential family whose maximum likelihood estimates are easily computed, then each maximization step of an EM algorithm is likely easily computed. Okay. And then they say, the term incomplete data is in its general form implies the existence of two sample spaces, y and x, and many one mappings from x to y. The observed data y are a realization from capital Y, and the corresponding x is in capital X is not observed directly. So here, when they say x and y, they mean x is like the data, the complete one, and y is like maybe a subsampling of it, or something that is like x but missing, right? So if you have y plus something else, you get x, right? That's how I get it.
Daniel, I think that the simpler example of it is Gaussian mixture. You can assume that you have a Gaussian mixture of, say, 3 Gaussians, and you get only samples from the Gaussians, and you have no idea what is the probability of each Gaussian. So what is missing here is some latent missing variable which tells you what is the probability distribution over the data sources, over each of Gaussians.
So what's the weight of each Gaussian, right? In a sense.
You also don't know what is mu and sigma of each one, but if you know the probability of each Gaussian, the life would be much easier. But you don't. In many cases, you don't.
Yeah. Thank you for that, Mike. That's a lovely example. And I've emphasized that because when I was reading it, usually in my mind, there's x and then y of x. So to me, it's like there is some kind of transformation between them. So it's confused me, right? But your example is spot on.
There is some transformation. You can just observe it in an implicit form. You get some data. I think the easiest way to look at it is just to assume that there is some latent, not known variable underlying your distribution. Actually, you don't need this underlying variable in many cases, the distribution of it, but via this latent variable, you want to learn the distribution of your data. But in some cases, you also need the latent distribution, but not always. This is so it is some implicit, some implicit mapping. The next one.
And then I think that's what they're gonna say now. They say we postulate a family of sampling densities f of x given phi or phi. Which letter is that?
That's phi, yeah.
Phi, okay.
Phi, yeah. That's the Greek letter phi, but in America you say phi.
Oh, so okay, cool. So phi.
You were right twice.
Yeah. How do you call
my T now. I should speak as an American.
Nir, how do you call a Greek letter phi? If you call phi, so how do you call phi?
There is no Greek letter phi.
No Greek letter phi?
There is psi and xi. There is no phi.
Psi. Okay, wow. Greek alphabet is not easy.
Okay, so I'll read it again. We postulate a family of sampling densities f of x given phi, depending on parameter phi, and derive its corresponding family of sampling densities g of y given phi. So again, x is the complete data, y is the incomplete. The complete data specification F is related to the incomplete specification G by, so how G and F are connected. Eventually, it's integral over all the possible x's over f of x given phi, and you get g of y given phi.
Yeah.
Can you give near some kind of intuition what's happening here? What is this integral?
Yeah, this integral is marginalizing x. That's it. So think about x, y as a subset of x.
Mm-hmm.
Okay, not only one-to-one relationship. It can be that x has, let's say, 1,000 measurements, and y is just the sample mean. Okay, of
Mm-hmm.
these 1,000 measurements. So if you want to get the probability density function of another variable from the probability density function of everything, you integrate by the variable you want out, right? You marginalize the function, and that's what they're doing here, I think.
Yeah, I think I'll add a very small remark. You're just integrating over all unobserved possibilities of the variable x, and what we're doing, you're trying to estimate what is the probability for each unobserved variable x. What is the probability to observe y, which we observe? Okay, too many observe. I think it is a bit clearer now.
Okay, I get the marginalization claim, and they say the EM algorithm is directed at finding a value of phi which maximizes g of y given phi, given an observed y. But it does so by making essential use of the associate family f of x given phi. So they say each iteration of the EM algorithm involves two steps, which we call the expectation step, E step, and the maximization step, M step. The precise definition of these steps and their associated heuristic interpretation are given in section 2 for successfully more general types of models. And here they're going to present an example. Okay, let's go to the definition. It's chapter number 2. They call it definitions of the EM algorithm. And they say, we now define the EM algorithm starting with cases that have strong restrictions on the complete data specification, then presenting more general definitions applicable when these restrictions are partially removed in two stages. Yeah, I'm not sure I want to go into all of the derivations.
Taking into account that there are some errors in these derivations, I'm not sure that it is.
Okay, so let's do this. Mike, tell then to our listeners what are the two steps. Why there's expectation, and then why then maximization.
I love to discuss this expectation maximization algorithm in the context of some latent variable z, which we don't know, but we're trying to estimate it. And this, but with the help of this latent variable z, we will estimate our observed variable x. Okay, they use y, but in almost any paper I read, they use z, so it is more comfortable to me to use z.
The y is confusing here, I agree.
Yeah, y is confusing because in every place you see, and almost every blog, almost every paper discussing expectation maximization, you see z as a latent variable. And what is the e step? If we assume some distribution of the latent variable, we want to estimate the probability or the likelihood of the observed data. So, for example, we start from some values which characterize this latent variable z. For example, for the Gaussian mixture, we can start from the probability of 1/2 for each Gaussian. If you have 3 Gaussians, you can start from the 1/4 probability of each of it, and then you compute the likelihood of your observed data. Okay, for these given parameters which you choose in the first step, and then in the next step, the maximization step, you are maximize the likelihood of your observed values over these parameters of the latent distribution Z, and this way it is called optimization. And then you go back to the distribution of your observed data. You not distribution to computing likelihood of your observed data. You compute it, and then you maximize it. Then you compute and maximize, and that's why it is called expectation maximization.
It's iterative.
Yeah, it's iterative algorithm. I don't remember the convergent properties of this algorithm. I think in every iteration it can be proved, as mathematicians say, under some mild conditions. I don't remember what are these conditions, that the error estimation error or the likelihood is not decreasing. Okay, but it's not decreasing. It doesn't. It's not increasing. Sorry, it's not increasing. But the fact that it's not increasing does not mean that it is decreasing. So regarding the convergence, I think we have some kind of convergence for some families of distributions, but for other distributions under some mild conditions, you have non-decreasing likelihood. Okay, I hope it was.
I think that you can converge to like a local maxima, but not to the global maxima or something like that, right?
I think, by the way, for the Gaussian mixture, if you get some samples and you assume some predefined number of Gaussians, in this case, I'm not sure, but I have an assumption that it belongs to exponential family, and in this case, expectation maximization converges to the global minimum. But in other cases, we need to look more closely.
Got it. Yeah, I'm looking over the examples. They did a lot of analysis in this paper. It's really long. It's 40 pages. Yeah, like Nir said, it's a book.
Almost a book.
And not just a paper. And I have a question for you. So the first step is expectation. So calculating the expectation is like estimating, no? Like
you're estimating
doing an estimation phase. And then my question is that true? I can choose different estimators.
Yeah, the
right? Or am I missing something?
No, the only estimator you're using in this algorithm is the sample mean estimator.
I know.
Which is the expectation. You can.
Yeah, but
you're free to use whatever you want. As my advisor said, it's probably they won't put you in jail for that. but will it converge? Will it actually go to the maximum? I don't know. And this when you take the expected value of all of the distribution function or likelihood functions given the parameters, they show that if you then do maximization and reiterate, it will converge. It will converge to at least a local minimum or maximum in this case. And
Daniel, actually, if you assume some form of your distribution, of your latent distribution Z, and the dependence of the distribution of X by the latent distribution Z, I think the likelihood estimation, if you assume independence of your samples, the likelihood formula is fully determined by this assumption. But you need some assumptions for this distribution. If you assume, for example, not Gaussian mixture, you can, for example, you have mixture of some binomial distribution. So
yeah, exactly. It's something weird.
something discrete, okay? And you have some mixture of binomial distribution. You can assume 5 binomial distributions, and you can assume 15 binomial distributions mixture, and the formula in these two cases will be different. So under the assumptions of under the assumption of the form of the X distribution, under the latent Z distribution, I don't think you have any any freedom here. You just have to compute your likelihood. Maybe there is, if the likelihood computation is very complicated and is not given in its closed form, you can use some estimates. But in my personal, not my personal, I once used expectation minimization. It was some quite complicated case of Gaussian mixture. Then the data was mixed. It was a mix of Gaussian mixtures. So some the number of Gaussian distribution changed over the sample. It was some quite complicated time series.
Okay.
But if you have some simple case, so you don't have any freedom. In my case, I'm trying to play, to divide the interval of time in some parts and reach the number of Gaussian is more or less constant. I did some tricks in order to estimate this likelihood. But if you assume some distributions, no freedom.
Yeah.
Just have to use the formula. As far as I can understand. Nir, do I miss anything?
No, I don't think so. It's just I think that in terms of actually using it, it's pretty simple. It's the expected value is, for example, for Gaussian mixture model, the expectation part is just counting. It's just counting how many of the samples are in Gaussian 1, 2, and 3, and that will be the a priori probability for the mixtures. And then you maximize on sigma and mu, right? On the covariance and the mean vectors. And then you iterate between them. But let me ask you this, Mike, Daniel. Let's say I have an optimization problem with a lot of parameters, okay, that I want to optimize on. Now, if I go and do like brute force type optimization, then let's say I have 10 parameters. The space is 10 dimensional, right? So it's not brute force will take a long time. So what I can do, what I'm doing in practice sometimes, is I'm fixing all the others on the initial guess, and I'm optimized for one parameter. Then I'm fixing the rest, including the new found parameter, and optimizing the second parameter. It's like a coordinate descent type algorithm. And my question is, can this be considered as EM algorithm?
It's hard to say,
Because that's what the EM algorithm is. That's what they're doing. They're fixing the parameters on values, and
That's right.
And they're taking the expected likelihood, and then on the expected likelihood, they optimize for the parameters again, and so on and so forth.
They update the parameters.
Yeah, update is optimization. Yeah. They find new parameters for this specific likelihood function that is the expected of all likelihood functions, the expectation of all likelihood functions.
I think it can be considered as an EM algorithm, because EM algorithm is a very wide family of algorithms.
Yep, it's very general.
By the way, when I hear that you are doing something on one variable out of many variables, I'm starting to think about Gibbs sampling. Then you are trying, then you are sampling dimension after dimension. Although in this case there is no connection. Okay, it just came to my mind, but there is no connection. And by the way, then I'm talking about the wide family of methods which can be called, which can be regarded, referred to as expectation maximization. We have many algorithms which aimed and improving the convergence speed of the expectation maximization, because the convergence speed of EM can be slow in some cases. And as far as I remember, I learned it many years ago when I was in academia. It was more than 20 years ago, I guess. There are some algorithms. What I remember, there are some algorithm which is based on conjugate gradient. I don't ask me. I don't remember how it is used. But this conjugate gradient approach was used to accelerate the convergence speed of expectation maximization in some cases. Sorry. So
Cool.
your method can be called expectation maximization.
By the way, sorry, Nir, finish.
I think that the only time, I mean, practically using specifically expectation and then maximization is when I deal with GMMs, Gaussian Mixture Models.
Yeah.
Yes, I do this step-by-step iterative type of optimization a lot, but and maybe it can be called EM. I don't know, but the classical EM I used in GMM. Did you use it in any other cases, guys?
No, I use the expression maximization to estimate the GMM parameters.
Yeah.
By the way, guys, I think question to both of you. I think expectation maximization somehow relates to Bayesian method. It is not fully Bayesian method, but you have some parameters and you try to estimate it. You have maximum likelihood, and you don't use usually don't use maximum likelihood with Bayesian methods.
Yeah.
But still, this approach is, it looks a bit similar. It is not fully Bayesian, but in part it looks like some kind of Bayesian. What do you think?
Absolutely, yeah. You can instead of maximum likelihood, instead of maximizing an expectation on the likelihood, you can do the same on the posterior density, and then it will be Bayesian, right? I don't see the difference.
Okay, interesting.
The steps, I think the steps are what's important, and not because yes, you're right. Usually you connect EM to maximum likelihood, but it's not the only case you can use it.
Yeah, it's interesting.
By the way.
Okay. Yeah. Then I look in the formulas for expectation maximization. I can't help myself. I'm thinking about variation optimization, the kind of optimization we see in, for example, in variation autoencoder, because you have some latent variables. For example, what is variation autoencoder? You have some data, and you assume that your data was generated from some latent distribution, from which you don't know what is the distribution, with some transformation, and this transformation is a neural network which you try to train. Okay, so and you need to train the coder, and you need to train the encoder, and but in essence you have some latent distribution, and you don't know it, and you're trying to estimate it by maximizing the likelihood of your data, and by enforcing the distribution of the over the latent variable you chose. For example, in many cases it is just Gaussian with 0 and 1, or with 0 and I, the standard Gaussian distribution. So there is some similarity, these assumptions are quite similar, but you did it in a bit different way.
So I wanted to add something interesting. At the end of the paper, if you can see it, there's like the reviewers. and what they wrote. So it says discussion on the paper by the three authors. So the first professor that wrote his review is EML Beal. And he says, it gives me great pleasure to open the discussion of this lucid and scholarly paper on an important topic, and to thank all three authors for crossing the Atlantic to present it to us. At some point, he says, for example, these remarks explain why I'm less enthusiastic about the author's new terminology than I am about the technical content of the paper. So that's like some criticism
What does it
of
mean?
their paper.
Yeah,
I don't know what he means.
No, he means that it's. I think I read it as well. He calls it a chicken and egg problem. So what do you start with, the expectation or the maximization? Where do you start there? And he calls it the circular logic argument. There is some.
In conclusion, I'm happy to propose a vote of thanks for this paper in spite of its title. He doesn't like the EM.
EM just sounds better. EM sounds better than ME. There's just sounds better for me, at least for me. Maybe I just got used to EM and didn't get used to ME, but still, for me, it is just sounds better.
Look, listen, another review by Nelder. He says, there are times when it seems that our subject is becoming more and more fragmented, with people quarreling vigorously in smaller and smaller corners and becoming more and more isolated from each other in consequence. It is a particular pleasure, therefore, to be able to speak to a paper which seeks and achieves a synthesis by exhibiting diverse procedures as special cases of a general one. Lovely.
Yeah.
That's really nice.
The
vote of thanks was passed by acclamation.
By the way, guys, this is the same Nelder for Nelder-Mead optimization algorithm.
Oh, cool! I didn't know that.
Interesting. This is the stuff you don't see in the modern, at least deep learning papers.
No.
There's been some time.
Yeah. Cool. So, thank you, Nir. Thank you, Mike. Thanks to our listeners. Yeah, and we'll see you in a week. I'll be in New York.
Nice. All right.
Have a great week. Bye-bye.
Bye, guys. Thank you.